let's see you are executing a program. What happened in the program is we have these type of program. Let's say this is printing a hello world, and it is what will happen on that is we use a compiler, let's say the GCC compiler, to execute this hello.c file. After the execution, it will create the executable file, which is a.out. We'll run it with ./a.out, and once we'll execute this particular line, what will happen is your executable code will be loaded into the RAM or into the main memory, because we know that in the von Neumann architecture, the CPU is going to handle any of the program which is there in the RAM. So whenever you want to run any program or any process, it should be in the main memory. So what will happen here is this executable code will be sent to the RAM and in the main memory. And here this program is called process. What is a process? Process is a program under execution. So you see the process is inside the main memory. This is your main memory. And about the process, a program under execution is called a process. It should present in the RAM, comprises of executable instruction, stack, heap, state of the operating system in kernel, state, constant, register, list of open file, related processes. All these things are related to the process. So what will happen in the main memory for the process? Let's say we have this program. This is a program. Inside the program, there are some functions. There is the main function. There are some global variables and all. What will happen into the main memory is, in the main memory, we have 4 parts mainly. One part is called text, which is instructions. Another part is the data, where we'll store global or static data. Then we have a part heap, and we have a part of stack. Okay. These two, heap and stack, has the variable size. So heap could be increased or stack could be increased. So that's why there is a cap. Stack could be increased downwards or heap could be increased upwards. So there is a gap here, depend upon the program. So in the main, all the main part, which is the part of the instruction, will be loaded into the text part. Okay. So all these parts which are scan, there is a pointer, there is a function call, there is a print statement, there is a free statement. All those things are there in the instruction register. Now, what are the things which is there in the data register? We have some static or global variables. So we have call as a global variable. So that is coming into the data section. What are the things that is coming inside the heap? So inside the heap, we'll put those instructions which can generate the dynamic memory. Here, malloc function will generate the dynamic memory during the program execution. It will be there in the heap. Now inside the stack, different instruction, like we have the local variables and the function which is a recursive function will be there inside the stack, because we know that recursion can be handled through the stack. And in the stack also we have some local variable which will be present. So this is how your whole program will be put together into the memory. And this particular memory you can find inside the main memory, because all these will convert the program into executable program, and this executable program we are going to load into the main memory. Into the main memory, there are different spaces where these processes will be, the part of these processes will be there, because whenever a program will be under execution, that program is called process. There is a size called from 0 to max size, and this particular max size is for the XV6 system. The max size is this is the hexadecimal address code. This is the address for this max size, and for the Linux, this is the address for this max size. Okay. Now, as we have discussed, for the process or the program which is under execution is called process. For that, we have text, we have data, we have heap, we have stack. All these are called user process access or user space up to the maximum size. And beyond that, there is a kernel space or system space where kernel text, its data or device memories are there. So you can see that this particular maximum size is very based on the Unix operating system or your XV6 operating systems. And this particular space is user space where the process or the program under execution will be loaded. And all these different data structures will be used to put different instruction or different data, different functions related to any program. So we are looking to what do you mean by a process? So if we have a program and a program is going to compile, and after that it is going to generate an executable code. This particular executable code, when we run and when we write this particular statement into the terminal and we'll just put enter, the process which was there in the secondary memory, this executable code, which was still a program, will be sent to the RAM, which is in the main memory. So now this particular program is called process. So your program, which is there here in the secondary memory, this executable program is also a program. It is not a process. These two programs are there in the secondary memory. Now, after when we'll execute this particular code, so your executable program will be sent to the RAM, which is the main memory. Okay. Now, at that particular time, we can say that this is nothing but your program under execution. So the process is there in the main memory. That process is now called program under execution. So a program under execution is called process. The process should be present in the RAM, comprises of executable instructions, stack, heap, and state of the operating system. About this, we'll see shortly. State contain register, list of open files, related processes. So all these things are different attribute related to the process. Okay. So all these attributes are there. Means you have the executable code, no doubt. But this executable code also have different properties. Like you must have seen in the database management system, like we have the data actually and attribute related to the data. Here also we have process and there are different attributes which are related to the process. That is also there in the main memory. So that we'll see shortly. Now after that, so what is that process is? An operating system execute a variety of programs. So if your operating system is batch system, so that program is called jobs. Means one job at a time or one program at a time. When we have a time sharing system, that is in the category of multi-programming system, where multiple program can be executed. On that, this particular programs are called user programs or the tasks. Okay. Textbook uses the term job or processes. So in some textbook, this process is called job, and some textbook, the process has been written almost interchangeably. So what is a process? Process is nothing but a program in execution. Process execution must progress in sequential fashion. Means, let's say we have a program, and in this program, there are different lines of code. These line of codes are called instructions. So we have instruction 1, instruction 2, instruction 3, instruction 4. In that way, there are different instructions. So you see what it is saying, that this program, which is under execution, is a process, but inside the process also there are different instructions. So what it is saying, that all the instructions should be executing sequentially. Means first this instruction 1 will execute, then instruction 2 is going to execute, then instruction 3 is going to execute, then instruction 4 is going to execute. Depend upon your program sequence. So it is saying that this process is no doubt is a program under execution, but there is a constraint like process execution must progress in sequential fashion only. So there are multiple parts in the process. What are those? Program code, also called as text section, current activity including program counter. Program counter, I'll tell you in shortly what is that program counter is. There are some stack data structure which contain the temporary data. Generally in the stack we have recursive functions or the function parameter, return addresses and the local variable. And then we have a data section contain global variables or the static variables. These variables, once it is generated, it will be there during the program throughout. That's why it is written in some section, in the global variable or static variable. Then we have a heap data structure, which is required for the dynamic memory allocation. So in the program, if we have something which is executing in a runtime, which was not executed previously in the compile time, so those codes are there inside the heap. Now, what do you mean by a program counter here? Okay, what is this program counter here? So just now we have seen that a process should execute in a sequential fashion. Okay, process must execute in a sequential fashion. Okay, I'll tell you about the program counter later on, because right now you didn't understand, because before that we have to understand some more concepts. So I think this thing you have understood. Let's see all these things, means multiple part of the processor in terms of the diagram. So you see in the memory map we have, and this particular is actually not in the main memory. This particular is your you can say virtual address space. Okay, I'll tell you what do you mean by virtual address space is in the later section. See, there is some parts, like first part is the text part where your whole codes are there. Then we have a data part where we'll put the global variable or we'll put the static variable. Then we have a heap where we'll put the dynamic memory related code. And here we have a gap. This gap, I'll tell you shortly what is the meaning of that. Then we have a stack. Inside the stack, we'll put some recursive function or some sort of variables or parameter of the function. So the function parameter will be there. So all those things, all those related data are there in the stack. And there is a heap. And what is this? What is this? This section. This section is nothing but, you can see these are the empty spaces. And these empty spaces could be occupied either by heap or by stack. So you see, if there is more number of data in the stack, so it will go downwards, means it will occupy these spaces which are downwards. So let's say this is, now we have many number of data in the stack, so it will be occupied that. Or if we have many number of data in the heap, so it will occupy that portion, means it will go up. It is just like, let's say you are using one notebook for two subjects. So what you do is, first you, for the one subject, you will start from the beginning, and another subject you will start from the very last, right? And because you don't know that how many pages will be taken by first subject or the second subject, so you use like that, and somehow they will meet in between. So in the same way, heap is starting in that way, stack is starting in that way, and somewhere they will meet. If the program or the process has the data which is beyond the limit of these maximum limit allocated to the process, then some sort of fatal error will be occur, okay, because the memory is not there afterwards. So some fatal error or some sort of other exceptions is going to come. So yesterday I told you about this particular diagram. Let's see this again with the help of a program. So let's say this is the program, and that program I have compiled, and I have generated one executable program. This executable program I'll put into the memory map. So this is the memory map of the process. You can see that this is your virtual address space. So whatever addresses that will apply here in the memory is virtual address space. It is not the actual memory space, or not the physical memory space. Physical memory space are the memory addresses of the main memory. Okay. Here we'll just create the virtual address space for a process. So as we have discussed, we have mainly four parts: text part, data part, heap part, and a stack part. So in the text part, the whole codes are there, which is the text, all the instructions. Then in the data part, we have the global variable. So here, this is the global variable of the program that is coming into the data part. And if we have some sort of a static variable, it also come into that data part. So the data part is fixed. The text part length is also fixed, but the heap length is not fixed, as well as stack length is what we'll put into the heap. We are going to put dynamic memory allocation, or the code which will run into the runtime, like dynamic memory, or the memory which is going to be allocated at runtime. So those type of code will be there in the in the heap. So heap part is for the dynamic memory allocation. Then we have a stack. Inside the stack, we'll put the recursive function, we'll put the local variables, and we'll put some sort of parameters which we'll use in the function. So all these things are there in the stack. So there are two types of these data structures that will be used, heap and stack, into the memory map for process. Okay. There is another element which is called program counter. We'll see about it, what is the program counter is, in the later section of the lecture. Now this particular space, which is the maximum size, this maximum size is depend upon your operating system. So you see, in the Linux operating system, this maximum size is C00000000, and in the XVC operating systems, the maximum size of this particular virtual space is 8000000. This is in hexadecimal code. This is the maximum address space which is allocated for this process, this max size. Okay, this max size is equal to these in the different operating systems. Now, in each virtual address space, there is the space for the kernel also. So you see this, these are the part that we have seen till now. This is the part of a process. And for each process, we have text, we have data, we have heap, we have a stack for each and every process. And all these processes, when the processes will be generated, means the program under execution, right? So all the program will not create the process. And all the program will not have allocated all these data and the data structures. So this particular space from here to here is user process, and this particular space can be accessed by user process. Now beyond that, it will be accessed by the kernel. So there is the kernel space which is there. This is the maximum virtual memory space are there, which is again dependent on your hardwares, because we don't know that what is the maximum length that RAM can be accommodated. So what is the length of a RAM? It depends upon that. But it is written some maximum. So you can say this is a, you can say it is a max limit. Okay, so there is a maximum limit. And here we have some kernel data. And in that data also, we have some data structures related to the related to the process. So every process having all these properties, and some of the property values are there in the kernel side also related to the process. So there are some text, data, device memories. So what will be there, like what are the devices that a process is going to use, what are the data that will be used for those devices, or what are the text are there to use on those devices. All those things are there inside the kernel. We'll see this particular thing in very detail, that what are the different content related to a specific process will be there in the kernel side. We know that whatever is in the kernel side, so there are usual things like we have different device driver, we have different functions which are related specific to the operating system. We have different scheduling and managing and resource allocations algorithms for that. All those things are there. Apart from that, there are some data which is specific to a process, which is, it is also there inside the kernel part. Okay, that thing we'll see later on. You just understand that this particular part that we are showing here, this is not in the main memory. This is the memory map, but for the virtual memory. This is virtual memory space. Okay. Now after that, this virtual memory will be converted into physical memory space. That process we'll see, that mapping, how this mapping will be done, that we'll see later on. But now we are looking for different properties, different functionality, all those things related to a process. So we'll not going to elaborate those things which are not relevant right now. Now, what is a process again? So we can say that this program is a passive entity and your process is an active entity, right? Because why we say it is a passive? Because it is stored in the disk in your secondary device. But the executable file, which is a process, is the active part, and this is there in the main memory. And your program is there in the secondary memory. The program becomes process when executable file loaded into memory. Before that, we'll say it is a program. One program can be several processes. So one program may have different processes considering multiple user executing the same program. So if multiple user is executing the same program, so definitely one program may have different processes. Yes, it is possible. Let's say there are multiple users who are using one program. in a system. So this will execute, and this is also going to execute. And they are separately going to put their process or they are separately going to run their processes and in the main memory. So you can see that user 1, user 2, and user 3 is executing the same program and creating the processes, different processes from the same program only. That is possible in a multi-user operating systems. Now let's go to different attributes related to a process. So before that, what attribute we have to the program? We have program name, right? So let's say hello.c or hello.ccp. So it will tell is a C program or C++ program. And there is the property like when it is created or what is the size of that program. So all those things are there, all those the property related to a program. But what is the property related to a process? Because now process is a program under execution, right? So when a new process will be created, we have to give some sort of identities and we have to give some sort of properties, okay, by which we can differentiate between process and process. So we have created a process from a program, and this particular process will assign some sort of ID that is called process ID, right? So the first property of any process is a process ID or a process number, right? So this is the property of a process, because let's say what is your identity, right? So you will have some sort of unique number. Let's say in your driving license or in your Aadhaar card, they have given you a unique number. So that from that unique number only you can be identified. In the same way, the process also can be identified by their unique numbers, and that is called process number or process ID. Okay. Then the second property of a process will be is its state. So what is the state of a process? Whether it is running right now, whether it is waiting right now, or whether it is ready to run right now, right? So what is the state of a process? So about the state we'll see shortly. Then what is the other property? The other property is program counter. Okay, now here the terms come, program counter. So we will see in detail what we mean by this program counter is. Location of instruction to next execution. So program counter will have the location. Location means the address of the instruction which is executing next. So as I told you, one process will have many instructions, right? So program counter will hold the address of the next instruction which is going to execute. Getting it? Because we know that the process is going to execute its instruction in a sequence. So there should be some pointers which is pointing to the next sequence or next, what is my next instruction, right? So that's why the program counter is being used there, and it is very much useful. Then we have some sort of priority. Like what is the priority of a process? It is also defined by the operating system, that if a process will be created, that process is a user process or that process is a system process. If the process is a system process, so we'll give the more priority. If the process is a user process, we'll give the less priority. Or from those user processes also, which process is requiring much attention. So based on the priority only, we are going to execute those process. That's why the priority is also a very important thing into the process, related to the process. Then we have CPU registers, contains of all process centric registers. We have different type of registers which are there related to the process, and all those registers are there inside the, you can see these are related to the register. And let me tell you what is this, okay, so that you can understand. Now first let's talk about program counter. Okay. Let's first talk about program counter. In short, it is called PC. So what happened in the program counter? Program counter will put the next instruction which is going to execute. Let's assume that one process will have multiple instructions. Instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, instruction 6. This is process 1. Then we have some more processes. Let's say, because we are talking about multi-processor operating system where multiple processes are ready to run. Okay, there are some instruction related to another process. Let's say these are the instruction related to process 2. Now let's see, this particular process is a kernel process, and this particular process is, let's say, user process. Okay, by that we'll know that what is the priority, right? Because kernel process has more priority than user process. Now let's see, previously your user process is running into the CPU, and after this there is an interrupt occur, like software interrupt. So it is going to execute the system program, and system program or the system call is there in the kernel level. So it is going to execute this. So it is going to execute instruction 1 of system call, 2, 3, 4, and 5, and again at last we have, because we have handled the what handled the any type of interrupt, then what will happen is it will again go into the program, again go into the process. So how the CPU will know that what is the next instruction that I am going to execute? So that thing will be taken care by the program counter. Now what will happen is, just before leaving this program counter will put the next instruction address in its register, and whenever we'll go to the same process again, so we doesn't have to start from the beginning, we'll start from where we have stopped, right? So that in that for that purpose this program counter is very much useful. So I think this significance of program counter you understood, right? Now let's go about different type of CPU register. Now, what is CPU register? We have seen different type of registers like ALU, we have data register, we have that register, those register, we have different type of registers. Let's talk about one instruction. We have an instruction, and that instruction look like this: x equal to 5 plus 2, right? This is my instruction. Or you can assume that x equal to a plus b. This is your instruction. How this instruction will look like? It will be add a comma b, and will do move whatever this value is to x from ALU. Not ALU, that is your accumulator register, AU. Now what will happen here is, we have a register which is dedicated for X, another register which is dedicated to A, another register which is dedicated to B. The value of A is, let's say, 5, and value of B is, let's say, 3. Okay. Now what will happen is we are putting these value into the register, that is register into the CPU. So the same will be updated into the process register also, because we know that what should be the register value inside the CPU. So the same thing will be there in the process, related to the process. So assume that this is instruction 4. This is instruction 4. And just after the instruction 4, there is some interrupt that is occur. So we have to load these instruction. So instead of that, so in the process, what will happen is there is the register where the value has been defined for A and for the variable B. So these two are the registers. Register value that we are saving inside the RAM where your process is. So this is the property of a process, CPU register. And this is in the actual CPU. So now what will happen is your process 2 is going to execute. Let's say the instruction 1 of process 2 will be like this. So it will be like this, y equal to, let's say, z plus w. Now what will happen? These value in these register, some z value will come. Let's say z is 2 and w is 3. Or let's say we'll put other values, let's say 4. So what will happen here? Here, these value will be changed to 2 and this value will be changed to 4. Okay. Now the execution will be done and the value will be allocated to some value. Let's say the value is 2 plus 4 is 6. 6 will be allocated here, and this is the variable name will be different, right? So this is for y, and this is for y that is allocated. Now what will happen is after some time the same process is going to execute. At that time, how CPU will know that what is there in the register, right? So that's why this value will be taken from the process only, because if we're not going to save these values which was there previously for this particular process, will be lost. So what will happen is we have to put 5 here and we have to put 3 here, then only we'll get the actual value, which is 8. Otherwise we'll get the old value which was there in the system because of the previous process, that is 6. That's why this CPU register is also a property related to a process, which is very much useful. These things, these problem which is related to a process could be occur by multiple reasons. One reason is interrupt. Maybe hardware interrupt, maybe software interrupt, we don't know. Second reason that can come when we are using some sort of round robin scheduling. Means we'll give, let's say, 2 seconds to one process, then 2 seconds to another process, then 2 seconds to another process. So what will happen is P1 will get 2 seconds, maybe it will executing, let's say, up to instruction 4, and after that, let's say P2 will get 2 seconds, and then it will execute its one, and then P3 will get its second. So that in that way, when we are doing multi-programming, here also this problem can be occur. So that is called preemption. Okay, preemption means forcefully we are removing the program from the CPU and we are putting another program into the CPU. That is called multi. In that way, we have the concept of multi-programming that can be done. Multiple program could be run at a time. So one program is executing for some time, another program is executing some time, another. So in that way, multiple program or multiple process can be execute into the CPU. So these two are the reason why we need these CPU register. So that is a significance, or that is a usefulness of the CPU register. So I think that part is clear to all of you. Then we have CPU scheduling information. Means, yeah, the priorities. What is the priority of the process? It is again coming. scheduling queue pointers, where your queue is pointing to. Means the queue is pointing to which particular process, means which particular process will go next into the CPU. That thing will be there. Memory management information like memory allocation to the process. It is also important that what is my address, what is the actual address of a process. So that is also there, right? So that thing will be there in the process table. There is a table that we'll see later on that is called process table. In this particular table, there is a mapping between your virtual address space and your physical address space. Okay, and that is done by the some sort of memory management information. Now we have, after that we have some accounting information like CPU used, how much time my CPU has been used. It means that if I have a program and that program will need, let's say, 5 bus time of the CPU, then how many bus time has been left still now? Means how many bus time the CPU has been executed. Let's say 3. So 2 is left. So that value should be known to the process. Clock time elapsed since starting, means how much time I have been waiting for my execution. Let's say I come at time t0 and I'm waiting till time t5, and then only I'll get the CPU. So this time duration is my waiting time, right? And time limits. So what is my time limit? There is, for the real-time operating system, this time limit is also a property where a process is associated with its time. That at that particular time is the maximum time by which a process has to be processed. So that is also there. Then we have IO status information like IO device allocation. It is list of open devices and list of open files. So list of open devices means if a process is there, so it should have how many devices it is using. So there should be the devices which is used by the process, or there should be the files information which is used by the process. So the device information, what are the different devices which is used in the process, and what are the different files which is used in the process, should be also there in the property of a process. So you see how many properties are there. The first property is the process ID. Then we have different state of a process, program counter, priority related to the CPU scheduling, CPU registers, memory management information, account information. Then we have IO status information like how many open files are there and how many open devices are there, right? See, we have different registers also, that is called CPU register or general purpose register. General purpose register. That is also the name of these registers, which are related to the process. So you see, all these are the property of a process. That is also called context of a process. That is also called task control block. That is also called process control block. So there are different names related to these properties. So process has different attributes, right? And these attributes are also called what they are going to call context. They are also called process process control block. They are also called task control block. So it depends upon which book we are following, but all these are the name of the properties related to a process. And you see how it look like. So we have PCB of program 1. Then we have PCB, program control block of program 2. Then we have PCB of program 3, right? So all these are different PCB related to different programs. So there is some initial pointer which is pointing to the first. This is pointing to the next, and this is pointing to the, in that way, in the linked list way, all these processes will be there, and there are different properties of the process. Except process ID. Process ID is defined somewhere here. And there are different properties of the process, which is also called context. So when in a CPU, we'll put a program, let's say program 1, and after that we'll preempt the program 1, somehow preemption, yeah, because of this interrupt or round robin. We'll put the program 2. That process is called context switching. Means one program properties, we are putting another program properties. Means one program will be switched by another program. P1 was there previously, now we are putting P2. That switching from program 1 to program 2 is called context switching. When we switch from program 1 to program 2 in the CPU, this at that particular time is actually a waste of time, because at that particular gap, CPU is not doing anything. So in different architecture, we have to reduce that time, because it will take time of switching from one program to another program. Okay, that time should, where CPU is not doing anything. So to reduce the CPU waiting time, or to increase the efficiency of the CPU, the context switching time should be reduced. So I think most of the thing related to the process property we have covered. Okay. Now you just see what are the different process state that are there. So we know that what is the second property of a what is the property of the process. So this is another property of a process which we call process states. I told you that we'll see shortly. So these are the process states. Process state means a process could be any of these states. Like if we'll talk about you people, so what is the state of a person? What are the different state of a person? So a person is either active, right? Or it will be in a idle mode. Or it will be a sleep mode, right? So a person is either active, means he is listening my lecture, so and putting his head on the lecture. So a person is in active mode. If a person is attending my lecture but he is thinking something else, and might be he is sleeping at that particular time, not physically but mentally, that is called idle mode. Or a person is sleeping during my class. So you have three states that are there. In the same way, process is also having different states. Okay, so about these process states we'll see in the next class.